So, do a quick recap of the tests that we have so far. So tests for convergence and divergence of a series. First and foremost, we have the nth term test, or the test for divergence. So the nth term test or test for divergence only shows divergence. And you're definitely going to have a question like this on your exam, for sure. Only can show a series diverges. So and so here's the test, right? It's the following. If the limit of the sequence is not zero, including non-existing, right? You can have a limit that's like bouncing back and forth between -1 and 1. That's not equal to 0. So then you can say the series diverges. For example, the sum from n equals 1 to infinity of 3n squared plus -1 to the n over 5n squared plus 4n. That sequence, so I should say, the sequence a sub n equal to 3n squared plus -1 to the n over 5n squared plus 4n converges to 3/5. You can show it, right? The limit as n goes to infinity of 3n squared plus -1 to the n over 5n squared plus 4n. If you divide everything by n squared, not that you need to show that, I think, but if you do, dividing by n squared, you get 3 plus -1 to the n over n squared over 5 plus 4 over n. 4 over n definitely goes to 0 as n goes to infinity. And -1 to the n over n squared bounces back and forth between 1, positive 1, 1, positive 1, sorry, 1, positive 1, -1, positive 1, -1, positive 1, but the denominator is still getting larger and larger and larger. This is like -1 over 1, and then positive 1 over 4, then -1 over 9, then positive 1 over 16, getting closer and closer to 0. So since the sequence converges to not 0, the series must diverge. Great. So nth term test for divergence can only show divergence. Put my water behind it did. That's a bummer. I didn't even leave it. Oh wow. Well, be thirsty for the next 45 minutes. Fine. So questions about this? Because the sequence converges, or the sequence does not converge to 0. So again, when the sequence is converging to something like 3/5, what we're thinking about is we are adding up 3/5 or something close to 3/5 or something close to 3/5 an infinite number of times. And when you do that, if the thing isn't getting closer and closer to 0, then the series adds up to infinity. That's the gist typically. So just as another example here, kind of a counter example, if I have the sum from n equals 1 to infinity of 1 over n, I couldn't use the nth term test. Or if I tried to use it, if I tried to apply the nth term test, I would get the limit as n goes to infinity of 1 over n equaling 0. And when the sequence converges to 0, it means we don't know anything about the series.
Inconclusive.
This test, yes, the nth term test is inconclusive for this series. That doesn't mean we can't find out what that series does. It just means the nth term test will not tell us. Instead, for something like this, we would use a p-series, which we'll get to in a minute. So the second test we should have in mind is geometric series test. So very generally, it looks like this. If the sum from n equals, doesn't really matter where you start, to infinity, some a times r to the n, this converges if the absolute value of r is less than 1. This diverges if the absolute value of r is greater than 1. So for example, the sum from n equals 4 to infinity of 5 times 2/3 to the n converges. Because the absolute value of your ratio is 2/3. And the absolute value of that is definitely less than 1. And additionally, we can find what it converges to. So I should also point out as a side note over here, if your ratio is between -1 and 1, then the series converges to the first term over 1 minus the ratio. So in this particular example, this series from n equals 4 to infinity, 5 times 2/3 to the n, converges to, well, the first term is 5 times 2/3 to the 4th over 1 minus 2/3. And I would leave it like that. At least I would start on an exam, I would start leaving it like that, do other stuff, but have time at the end and might consider simplifying it. If you see a question that says, what does the series converge to? It's a very good clue that it's probably a geometric series, because that's the only kind of series he's really talking. Well, I guess he's talking about partial sums a tiny bit, but mostly it's these ones here. Yeah.
Quick question, like the professor explained the series to be like the first term times 1 minus ratio to the power of number of terms over 1 minus r. I was just wondering what.
Oh, sure. So he's finding the nth partial sum there. Let me take a look real quick. Sure. Yep. Right, because he's not actually he's not finding the infinite sum there. He is finding a partial sum, right? He's going so far. And so, yeah, the formula for that is a little bit different, which I'll get to in a minute, but let's deal with this for just a second. We'll come back to that. So alternatively, we could say that something like this, the sum from n equals 2 to infinity of, I don't know, 4 times 3 to the 2n over 5 to the n. Although this looks kind of sneaky, like it might converge because it looks like your ratio might be 3/5, it's actually not. This is equal to the sum from n equals 2 to infinity of 4 times 3 squared to the nth power for 5 to the n. Or as I would write this, the sum from n equals 2 to infinity of 4 times 9/5 the nth power. Oh, my ratio here is 9/5. And the absolute value of that is bigger than 1. So this definitely diverges. Cool. We will get back to your question, Hanson, but I just want to write down this one more test here. The next one, which always kind of feels unfortunate when you think about it with the geometric series, because it kind of feels like the conditions are kind of opposite of each other, but we have to get them down. So the next one is a p-series. P-series just says, if you have the sum from n equals 1 to infinity of 1 over n to some power, this converges if that power is greater than 1. This diverges if that power is less than or equal to 1. The way I kind of think about it is, for it to converge, the terms have to get small fast. And if your power is larger than 1, then the denominator is growing more and more quickly. So for example, the sum from n equals 1 to infinity of 1 over n to the 5th power definitely converges. Because you're adding up, you get the sum from n equals 1 to infinity, 1 over n to the 5th is 1, plus 1 over 2 to the 5th is 1 over 32, plus 1 over 3 to the 5th is 1 over 243, plus 1 over 4 to the 5th is 1 over 1,000, right? The terms are getting really small really fast. On the other hand, something like kind of the classic example, the sum from n equals 1 to infinity of 1 over n diverges. The terms are not getting small fast enough. Even though the terms are going to 0 eventually, 1 plus 1/2 plus 1/3 plus 1/4, those terms are just too big. They add up to infinity. I know it seems like they might not, but they do.
Wait, so we see diverges bigger than 1.
Diverges if p is less than or equal to 1. Right, so if the bigger this power is, the bigger the denominator is going to be. And when you have a bigger denominator, you have a smaller overall fraction. So these terms, right? I mean, compare these terms. What's bigger, 1 over 32 or 1 over 2? Right, it's way bigger than 1 over 32. It's like 16 times bigger. Right, 1 over 32 is a thin slice of your pie. 1 over 2 is half of the whole pie. Same deal, right? 1 over 243 versus 1/3. Right, so these terms are getting small super duper fast. So when we add them all up, it doesn't add up to much. It adds up to, I don't know what this converges to. I know it converges. I don't know, and I expect to know what it converges to. Versus these terms here, they still get smaller, right? 1/3, 1/4, 1/5. The sequence here converges to 0. The series here diverges. Okay, do you have a question?
Oh, yeah. Very what can you do with these type of situations?
Mhm.
And you can invest guessing that like the pieces, for example, it's really adds up power or something.
Right, it's 1 over n to a power. Yep.
So that,
Yeah. And 1 is the breaking point. 1 over n diverges. 1 over square root of n diverges. Right here, p is equal to 1. Here, p is equal to 5. Here, p is equal to 1/2. So p is less than or equal to 1, series diverges. P is larger than 1, the terms get small fast enough, and series converges. Yeah. So if p is smaller than or equal to 1, like 1 or 1/2, the series diverges. Literally, the terms add up to infinity. Whereas if p is larger than 1, then the terms of the sequence get small really fast, and the series itself converges to some finite value, which we don't know. Except for like 1, we know the sum of 1 over n squared adds up to pi squared over 6. But other ones might be known. You don't even know. I don't even know. Nobody needs that. So, and then we have the comparison test. The comparison test says here's the words that I'm going to say, and I'm writing down some stuff. If your series is bigger than the divergent series, it also diverges. If your series is smaller than the convergent series, it also converges. So here's the way we write this out kind of longer. If an is smaller than or equal to bn, and the series for bn converges, then so does the series for an. What you're essentially saying is this adds up to something finite, and this adds up to something less than that. I forgot to write one important thing. The ANs do need to be non-negative. So if you have a bunch of things that are positive, and they're less than or equal to a bunch of things that are positive that add up to a finite amount, then they are also going to add up to a finite amount. And then on the flip side, if an is bigger than or equal to some other sequence Cn, and it's always non-negative, and the sum of the Cn series diverges, I am thinking here adds up to infinity. If I add a bunch of terms and they add to infinity, oh, I forgot to on my screen. Sorry, I mean my video. Not that it's super important, but it's weird when there's no face, I think. Anyway, when a bunch of things add to infinity, and then you're adding up a bunch of things that are bigger than all those things, well, they're also going to add to infinity. For example, I want to show that the sum from n equals 1 to infinity of 1 over n to the fourth plus 3 converges. Or really, the question actually is going to be determine whether the series converges or diverges. And the hard part about using the comparison test, is you have to decide before you do anything. Do I think this series converges or diverges? Usually, you're going to think about comparing it to a p series. If I compare this to p series, and you're like, yeah, that looks a lot like 1 over n to the fourth. So I'm going to compare this to the series from n equals 1 to infinity of 1 over n to the fourth, which we know is a convergent p series. For the comparison test to be useful at all, our series, if we're trying to show it converges, has to be less than the thing we're comparing it to. So is it true? And it is. The sequence we're looking at, 1 over n to the fourth plus 3. Well, first of all, it's for sure always positive, right? All those terms are always positive. And it is also true that it is less than 1 over n to the fourth. Because if my denominator got larger, and it did, then my overall fraction got smaller. So since that's true, then we can say that our series from n equals 1 to infinity of 1 over n to the fourth plus 3 converges by comparison.
So when you're when you see like 0 is less than the little value less than.
Right. Well, so here's, well, it depends. Depends on what I'm trying to show. So if I'm trying to show convergence, I want the unknown one to be less than the known one. Well, I would say it's a known series. So this series, we know it's convergent because it's a p series. It's a p series where p is bigger than or equal to 1. On the other hand, I could also say I want to show the sum from n equals 1 to infinity of 1 over the square root of n minus the half, I guess, just to be easy about it. I want to show that this diverges. To show something diverges using comparison, I have to show that it is larger than some other known divergent series. So I'm going to compare it to, well, this looks like 1 over n to the 1/2 essentially. So I'm going to compare to the sum from n equals 1 to infinity of 1 over n to the 1/2. And I know that this is a divergent P series. Right? That is a P equal to 1/2, which is less than or equal to 1. So here it was a P equal to 4, which is bigger than 1. And now I have to double check though. This is what I want to compare it to, but is that actually bigger than that? Well, yeah, it is. Note or observe that the unknown series, I should say the sequence for the unknown series, 1 over the square root of n minus 1/2, is definitely larger than 1 over n to the 1/2, or 1 over the square root of n. If my denominator gets smaller, my overall fraction gets larger. And then it's also worth mentioning, yeah, 1 over root n is still bigger than 0. Because the thing about these two tests is they're tests really only for when all the terms are all positive or non-negative. So then, because the unknown right here, so here the unknown one needs to be bigger than the known one. And then we can say, great, that shows that the unknown series from n equals 1 to infinity of 1 over the square root of n minus 1/2 must, diverge by comparison. No, no, it will not. Well, I should say, generally no. Usually through the comparison test, that's the hard part about the comparison test, is you have to come up with the thing to compare it against.
Oh, but then they'll like tell you to show it divergent.
Probably not. So it depends, and I don't know what, but and your teacher doesn't give practice tests, so. But usually, when I would write tests like this for when I taught this class, I'd be like, determine whether or not the following series converge or diverge, using whatever appropriate test, and also state the test you are using.
Oh, but then they'll tell you which test to use.
No. Yes. But there's some hallmarks to look for. So if you see, well, first of all, you should always think about using the test for divergence. Does the sequence converge to 0? If yes, proceed. If no, it diverges. The series diverges. Right? That's always at the forefront of my mind. Well, maybe it's at the back of my mind, but it's always there. I'm like, oh, I should check the limit of the sequence. Is it 0? Okay, then I'll try something else. Is it not 0? Great, I am done. That series diverges. And I almost can guarantee there'll be at least one question on your exam that will end up diverging by the nth term test. For sure. It's practically a given. But then look for something where you see stuff raised to the nth power. That's probably going to be geometric. Now, I'll point out, you can't have any other n's. You can't have like 3 to the n over n. That won't work out. Yeah. We did. Well, and yeah, I'll get that set. And then so I'll say here, right, look for 1 over n raised to a power, like the 3rd or the 4th or the 5th. That's a P series. We know when those converge and when those diverge. And then yes, comparison test, I'm looking to compare against really one of those 3 things. 2 things, really. I'm usually comparing against a P series that I know either converges or diverges, or maybe a geometric series like in this next example. Let's say I want to show that I want to determine whether or not this series from n equals 1 to infinity of n squared over 5 to the nth power converges or diverges. And it definitely doesn't diverge by the nth test. If you take the limit, as n goes to infinity of n squared over 5 to the n, it's going to equal 0. And you can either justify that to yourself by saying the bottom thing is an exponential function. And exponential functions always overpower polynomial functions. You could also use L'Hopital's rule twice. But it's 0. Which tells us nothing, right? This means great. Do more work. Okay, but here's the problem. It's not geometric, and it's not a p-series. Right, to be geometric, everything has to be raised to the nth power, and having an n squared is not going to work. You could also start writing out terms if you wanted to. If I write out terms, that helps me see it's not geometric. My first term is going to be 1 over 5. My second term is going to be 4 over 25. My third term is going to be 9 over 125, and so on. And I'm definitely not multiplying by the same ratio each time. 1 over 5 times 4 over 5 gets me from there to there, but 4 over 25 times, it's not times 4 over 5. 4 times 4 is 16. That doesn't get me 9. So definitely not 4 over 5. So it's not geometric. But really, when I'm looking at this, once I see an n that isn't my exponent, that tells me it's not geometric. So what would I do here? Well, I think I can figure out a comparison, because I think it's true that n squared is less than 4 to the nth power. Now, how do I know to do this? Because I've practiced it. Well, let's check. If n equals 1, I get 1 less than 4. If n equals 2, I get 2 squared less than 4 squared. If n equals 3, I get 2 cubed less than 4. Sorry, 3 squared less than 4 cubed. If n equals 4, I get 4 squared less than 4. Yeah, I think we're safe, right? Because then afterwards, I'm just multiplying by more over here then. Okay, so now check this out. Saying this means I can then say this. N squared over 5 to the n is less than 4 to the n over 5 to the n. And we know that the sum from n equals 1 to infinity of 4 to the n over 5 to the, calm down, Siri, oh my gosh. 4 to the n over 5 to the n is really the sum from n equals 1 to infinity of 4/5 to the nth power. What kind of series is that? Yeah, it's totally geometric. This is is it a convergent or a divergent geometric series? Right, this is a convergent geometric series. And we can show that this converges by saying, well, I said we've done enough now. So since our sequence is less than that sequence, then we can say by comparison, this sequence, sorry, this series from n equals 1 to infinity, n squared over 5 to the n, well, it's less than the series of a convergent geometric series. So by comparison, this must converge. Because I knew what I was doing. Really, I'm not going to lie. So I was going to do a different example, but it doesn't work out as well. So there's another example of this where it's like n squared over 3 to the n. And you can kind of compare it to 2 to the n over 3 to the n, but it doesn't work out as nice because not all the terms are less. So I chose that because I knew it was going to be less. Now, let me tell you, this is probably not the way you want to do this, even though you can. Because although you can do this, usually if you see something raised to the nth power, and it's not just a straight up geometric series like we would like it to be, instead of trying to find something, right, I had to work it out ahead of time what I was going to compare this to. Like I could have tried 3 to the n, but that wouldn't have worked exactly. I could have tried other things that don't work. But instead of doing any of this, I'm usually not trying to use the direct comparison. Instead, what I would rather do for something like this, from n equals 1 to infinity, of n squared over 5 to the n. So here is kind of the thought process I would say. If we see, sure, fine, too easy to do either. If we see something raised to the nth power, and it's not geometric, and it's not exactly geometric, or even if it is, actually, doesn't actually matter. If it is straight geometric or not, you can still apply the ratio test. So when I'm thinking about the ratio test, I'm thinking, do I have something raised to the nth power, or do I have an n factorial? Those are the two instances where it is almost always appropriate to use the ratio test. If you've already excluded the fact that it's geometric, right? Because if it's geometric, you just know it. Nothing, and you certainly can use the ratio test if it's geometric. You're just doing more work than you need to do. So here, and I know we haven't talked about the ratio test, but we're going to talk about it right now. So the ratio test says you take the limit, as n goes to infinity. Technically, there's an absolute value of the n plus 1 term over the n term. So in this case, it's going to be the limit n goes to infinity of n plus 1 squared divided by 5 to the n plus 1 over n squared over 5 to the n. And I dropped the absolute values because I know everything's already possible. And here's what I'll say about this. I almost always skip this step. I would say I'm usually going to start out at this next step, which is the following. The limit is n goes to infinity of my an term, n plus 1 squared over 5 to the n plus 1. And instead of dividing by an, we're going to just multiply by the reciprocal. Because it's almost always going to be a fraction. So we're going to multiply by 5 to the n over n squared. So right here, there's your a sub n plus 1. And right here, there's your reciprocal of a sub n. Same thing. But I know I'm always going to end up doing this because I want it to work out. I want it to look nicer. And then the next step is usually to kind of group the like things together. So I'm going to rewrite this as the limit as n goes to infinity of n plus 1 squared over n squared times 5 to the n over 5 to the n plus 1. Okay, simplify a tiny bit. N plus 1 squared over n squared, those are both raised to the same power. So I could actually write this as the limit as n goes to infinity of n plus 1 over n squared. What's 5 to the n divided by 5 to the n plus 1? It is 1/5. Right? Subtracting those powers, you got 5 to the negative 1, which is 1 over 5. And now if we take the limit of this part, well, if I look at the insides here, n plus 1 over n, that's just the usual, I've got a rational function, the degree on top and the degree on the bottom are the same. The limit is the quotient of the leading coefficients, which is just a 1 over a 1. I'll point out something that's generally true. When you have something like this, where you have an n squared or an n cubed, that part almost never contributes anything. It almost always just ends up being a limit of 1. We'll see it again in the next example. So here I get 1 squared times 1/5, which is equal to 1/5. And if that ratio is less than 1, which it is, that means the series converges. So 1 second. So we can say that the sum from n equals 1 to infinity of n squared over 5 to the n converges. Sorry, remind me of your name. Justin. What's up, Justin? Sure. So a reminder, when you're writing out this series, we are saying very generally it's the series from n equals 1 to infinity of an. We were just calling the sequence that we're taking the series of a sub n. And so in this case, a sub n is n squared over 5 to the n. And a sub n plus 1, it's like a function. I'm just replacing n with n plus 1, and I'm getting n plus 1 squared over 5 to the n plus 1. That's what's happening there. The great thing about the ratio test is you don't have to have an opinion about whether or not you think the series converges or diverges. You just apply the ratio test and you get a result. Although you can get an incomplete. So let's write down what the ratio test says, and then we'll do a few more examples. So the ratio test says the following. Good, Hanson? Cool. All right. So the ratio test says for a series from n equals, it doesn't really matter, to infinity of a sub n, we take the limit. The limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And you're going to get some number, possibly infinity. If that number is less than 1, you get convergence. If that limit is larger than 1, you get divergence. And if that limit is equal to 1, we are sad. That means the test is inconclusive, which means you have to do something else. So those are the three things that can happen. The more important thing I want to point out is, when do we use the ratio test? Well, technically, you can use it whenever you want, but the time it's going to work the best is if you see something like 2 to the n, or 3 to the n, or something to the nth power, or any sort of factorial. You see anything like that, those are excellent times to use the ratio test. On the other hand, the ratio test absolutely fails to be useful at all if you're trying to use it for a p-series. For example, sum from n equals 1 to infinity of 1 over n squared plus 1, which we could totally show converged if we just used the direct comparison. But instead, if I try to use the ratio test, you might not want to write this down. You totally can, though. If I use the ratio test, I'm going to do the limit as n goes to infinity of the n plus 1 term. So 1 over n plus 1 squared plus 1. And instead of dividing by the nth term, I just like to multiply by the reciprocal of the nth term. I'm going to multiply by n squared plus 1 over 1. Here's my a sub n plus 1. Here's my reciprocal of a sub n. Okay, but then look what happens when we simplify this. This becomes the limit as n goes to infinity. I actually don't really want to multiply it out, although I will if you want me to. On top, we just have n squared plus 1. On the bottom, we just have n plus 1 squared plus 1. And highest power on top is n squared, highest power on the bottom is n squared. Coefficients are 1 over 1. That's going to be a limit of 1. But you could multiply it out. I don't think you need to. If you multiply at the bottom, you get n squared plus 2n plus 1 plus 1. And then you get a 1 over a 1. That's equal to 1. Inconclusive. So what I want to point out is you don't want to use the ratio test if you have n squared or n cubed or just n to powers and not something raised to the nth power or something with an n factorial. But I said I was going to give you another example of the thing. Sorry, brain. Oh yeah, sure. So let's say we have the following. And this comes, so let's say we want to find whether or not the series from n equals 2 to infinity of, sure, n factorial over 3 to the n times n to the 4th. Converge or diverge? Okay, I see all the hallmarks that make me think I should. Okay, if you see a factorial, the ratio test is equal. A factorial automatically interesting. Even if you have something to the nth power, that almost always means automatic. So I'm just going to throw it, and I'm right. So I'm going to write the long way. There's my a sub n. I'm going to do the limit. N goes to infinity of a sub n plus 1 over a sub n. I would normally skip this step, but I want to write it out just so everyone can see it. So my a sub n plus 1 is going to be n plus 1 factorial over 3 to the n plus 1 times n plus 1 to the 4. And then my a sub n is going to be just what already is written there. N factorial over 3 to the n times n to the 4. Technically, there should be absolute values around all this, but since everything is already always positive here, I don't need them. The only time you really need absolute values is if you've got like something that's alternating, like you have a negative 2 to the n, and then you do need the absolute values, which I'll do an example of. Yeah, we got time. So This is going to be the limit as n goes to infinity. Here's the actual first step. I would encourage you all to have written n plus 1 factorial over 3 to the n plus 1 times n plus 1 to the fourth times the reciprocal of the denominator. Right? We flip and multiply. You get 3 to the n times n to the fourth over n factorial. And then just like the previous time, we're going to group the like things together. This is always the way to go. You want the factorials together. You want the things raised to the nth power together. You want the things that are powers of n together. So I'm going to write this as the limit as n goes to infinity of n plus 1 factorial over n factorial. No, we can't just cancel the factorials. They do not cancel. And then we have 3 to the n over 3 to the n plus 1. And then we have n to the fourth over n. Okay, so let's deal with the easy parts first. 3 to the n over 3 to the n plus 1 is just 1/3. Here we're going to group this together, but we can't. We'll say something. We'll leave that alone for a second. So what about n plus 1 factorial over n factorial? Yeah, you just like before when you had 5 to the n or 5 to the n plus 1, you told me it was 1/5.
Oh, yeah. But isn't it really?
It's 3 to the n over 3 to the n plus 1. There's one more 3 in the bottom. But for n plus 1 factorial over n factorial, let me ask you all a question. Well, I wouldn't say it that way. I want you to be a little bit more thoughtful about it, but you're not wrong. But let me show you the more general thought process. What is 5 factorial divided by 4 factorial? Right, because 5 factorial really means 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. Or if you prefer, you could write the top as 5 times 4 factorial over 4 factorial. And then the 4 factorials cancel out. You just get 5. And you're right. Very generally, n plus 1 factorial over n factorial is going to be, well, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And n factorial is the same deal. It's n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Or a nicer way of writing it would be n plus 1 times n factorial over n factorial. And then yes, the n factorials cancel. So n plus 1 factorial divided by n factorial just gives you an n plus 1. So here's what we've got now. We've got the limit, n goes to infinity, of n plus 1 divided by 3 times n to the fourth over n plus 1 to the fourth. And since these n plus 1s happen to be the same, I can actually cancel one of them out. I can cancel one of these here and one of those there. So look what I've got now. I've got the limit, n goes to infinity, of n to the fourth over 3 times n plus 1 cubed. And when the power on top is higher, the fraction is getting larger and larger and larger. The limit of this is going to be infinity. Let me do a little more work. Right. You got n to the fourth over 3 times n cubed plus 3n squared plus 3n plus 1. But the top is definitely getting bigger faster. If you really want, you can show the work of dividing the top and bottom by n cubed. And then if you do that, you've got the limit, n goes to infinity, of n on top over 3 times 1 plus 3 over n plus 3 over n squared plus 1 over n cubed. And 3 over n goes to 0, 3 over n squared goes to 0, 1 over n cubed goes to 0, and n goes to infinity, and infinity divided by 3 is still infinity.
Would we have been able to like divide by n cubed and I was still like in the top one?
Like here? Yeah, you can do it that way. You could tell, you could say the limit n goes to infinity, n to the fourth over n cubed over 3 times n plus 1 cubed divided by n cubed, and that ends up being the limit then goes to infinity of n on top 3 times n plus 1 cubed over n cubed is n plus 1 over n, which just becomes 1 plus 1 over n cubed. And yeah, this part still goes to 3 on the bottom and 3 on the top. Now, I don't think you need to show any of this work actually. I think once you get to this spot right here, and you recognize that the degree on top is higher than the degree on the bottom, that is the perfectly fine place to usually jump to the conclusion that it's going to be infinity. Okay. There was something else. Here. One second. All my examples. Cool. Not what I was looking for. All right, fine. So let's look at, we got time for one more. There we go. Yeah, let's look at this one. Let's say we have, I want an alternating one. Yeah, sure. Let's say we have the sum n equals 1 to infinity. Seems complicated. So let's do -5 to the n times n cubed over n plus 2 factorial. Again, I'm seeing all the hallmarks of a ratio test here. I got something raised to the n, I got something factorial. So we're going to use the ratio test. It's definitely a good idea to write what test you were using when you were taking an exam, so someone knows what your thought process is. All right, limit n goes to infinity. I do need the absolute values here because I have something that's going to be negative sometime. So you get -5 the n plus 1 times n plus 1 cubed over n plus 1 plus 2, so n plus 3 factorial times the reciprocal of this, so n plus 2 factorial over -5 to the n times n cubed. Right, this is your a sub n plus 1, and this is your reciprocal of a sub n. Okay, so simplifying, limit n goes to infinity of the absolute value of -5 to the n plus 1 over -5 to the n plus 1 cubed over n cubed, n plus 2 factorial over n plus 3 factorial. What's -5 to the n plus 1 divided by -5 to the n? -5. What's the absolute value of -5? Right. So in the next step, I'm going to say that I'm going to drop the absolute values and just say I have a 5. Because the absolute value of -5 is 5. And everything else is positive. N plus 1 cubed over n cubed is n plus 1 over n cubed, whose limit is going to be 1. Right. Whenever you have something to a power over something to the same power, that's just the limit, it's just the quotient of the leading coefficients. The n to a power part, when using the ratio test, really never contributes anything. It's always just going to end up having its limit be 1. And then finally, n plus 2 factorial over n plus 3 factorial leaves us with what? 1 over what? N plus 3. So let me show you. N plus 2 factorial over n plus 3 factorial. N plus 2 factorial just means n plus 2, and then you have to start multiplying it by the next smallest term. So n plus 2 minus 1 is n plus 1. And n plus 1 minus 1 is n. And n minus 1 is n minus 1. N plus 3 factorial starts at n plus 3. And then the next term is n plus 3 minus 1, which is n plus 2. And the next term is n plus 2 minus 1, which is n plus 1. And you just keep getting one smaller every time. And then everything cancels except for the first term on the bottom. So yeah, it's going to be 1 over n plus 3. Okay, now not doing too much work because it is 2 p.m. If you multiply it out the top of this entire fraction, what would the highest power be? N to the 1. Right. You'd have the limit as n goes to infinity of 5 times n to the, because the 5 is out there too. I don't really care, plus stuff. If you multiplied out the bottom, the entire bottom, this times that, what would your highest power of n be? Not squared, a little more, right? Because this is an n to the third times another n would be an n to the fourth. So the higher power is in the denominator, which means the denominator is getting bigger faster, which means the overall limit is going to be 0. And 0 is less than 1, which means this converges by the ratio test. So if you end up with limits where you have higher powers of n on the top, the limit goes to infinity, the whole thing diverges. If you have limits where you have higher powers of n on the bottom, the limit of that is going to be 0, and the series is going to converge. All right, we'll talk more about the, well, I guess we'll like talk more about this / exam review on Wednesday.